Hello, Bacho, and welcome to the class. Today we're going to tackle a very important topic from your first chapter, electric charges and fields. The topic is forces between multiple charges. Now I know the name sounds a bit heavy, na? Multiple charges. But trust me, by the end of this session, you'll find it's one of the simplest ideas. And if you get it right, you're going to score full marks on any question that comes from this. Chalo, let's begin.
Okay, so before we jump into anything new, let's start with something we already know, something we're already masters of. And from there, we'll see where the real challenge begins. You are all experts in Coulomb's law, right? I know that. It tells us the force between two simple point charges, Q1 and Q2. Bilkul simple. But let's be honest, in the real world, when do charges ever come in nice, neat pairs? What happens when a whole crowd, a whole party of charges shows up? Suddenly you have Q3, Q4, Q5, all surrounding our poor Q1. So the big question is, how on earth do we find the total force on Q1 now? Does our good old Coulomb's law even work anymore? Now, I know what you're thinking. This looks complicated. But what if I told you the secret, the solution, is surprisingly beautifully simple? The golden rule is this. Don't get scared by the crowd. Just handle them one at a time. That's it. That's the entire magic trick for today's lesson. To really get this, let's picture a game of tug-of-war, okay? Imagine our charge, Q1, is a ball right in the center. All the other charges, Q2, Q3, Q4, they are like players, each pulling on the ball with their own rope in their own direction. Now tell me, where will the ball move? Obviously, it depends on the combined effect of all the pulls, isn't it? And here's the most important part. Just because player Q3 joins the game, does that mean player Q2 suddenly starts pulling weaker or stronger? No way. Each player's pull is their own private business. It's totally independent. So, this very cool and simple idea that you just look at one pull at a time and then add them all up, this actually has a formal physics name. And this name is very, very important for your exams. It's called the principle of superposition. Let's see what the official textbook definition looks like. Okay, so here it is, word for word from your NCERT textbook. It sounds a little heavy, I know, but don't worry. The entire meaning is hidden in just two key phrases. The first is vector sum, and the second is individual forces are unaffected. If you understand these two phrases, you've understood the whole principle. Let me break it down for you. So let's make this super simple. Point number one, individual forces are unaffected. This just means that the force between Q1 and Q2 is their own private matter. They don't care if Q3, Q4, or 100 other charges are watching. For that calculation, it's as if the others don't even exist. And point number two, vector sum. This is crucial. This is where students lose marks. You calculate the force from Q2, then from Q3, but you don't just add the numbers. You have to add them as vectors, respecting their direction. That's it. So how do we actually do this? Look at this picture. Let's say we want the total force on Q1. So for step one, just pretend that Q3 isn't even there. Poof, it's gone. Now it's just a simple problem with Q1 and Q2. We use Coulomb's law to find the force, F12, and we draw the vector. Done. Now for step two, we bring Q3 back, and we pretend Q2 has vanished. Now we find the force between Q1 and Q3, which is F13, and draw its vector. See? One pair at a time. So now we have two force vectors starting from Q1. We have F12 and F13. What's the final step? We just find their vector sum to get the total force, F1. And how do we do that? Remember the parallelogram law of vector addition from class 11? You just use that. You complete the parallelogram and the diagonal starting from Q1. That, my friends, is your final answer, the net force on Q1. All right, the theory seems clear, I think. But I know what you really care about is, can we solve the numericals in the exam, right? So let's create a simple, foolproof, step-by-step recipe that you can use to solve any problem on this topic every single time. Just follow these 4 golden steps, okay? Step 1, identify your target. The question will tell you which charge to find the force on. Let's say it's Q1. Step 2, pick one neighbor, just one, say Q2, and calculate the force F12 using Coulomb's law. Ignore everybody else. Step 3, repeat this process for all the other charges. Calculate F13, then F14, and so on, one by one. Step 4, the final step. You have all these individual force vectors, just add them all up using vector addition. That's your final answer. Simple and always correct. Okay, enough of theory. Let's actually put these steps into action with a very simple example. Ready? So here's a classic exam-style problem. We have three charges, Q1, Q2, and Q3, and they're placed at the corners of a triangle. Our mission, should we choose to accept it, is to find the total force acting on charge Q1. Now, just to make things really easy, let's say we've already done the calculations. We found that the force from Q2 on Q1, F12, is 5 newtons, and the force from Q3 on Q1, F13, is also 5 newtons. So, my question to you is the total force on Q1 simply 5 plus 5 equals 10 newtons? What do you think? Pause for a second and think about it. If you said 10 newtons, then you have just fallen for the most common trap in this entire chapter. This is what I call a silent killer, a mistake that silently eats up your marks in the exam. Let's make sure you never, ever make this mistake again. And here it is, the number one mistake. Just adding the magnitudes. 5 plus 5 equals 10. This is scalar addition. This is completely wrong. And why is it wrong? Because force is a vector, Bacho. It has direction. You cannot just ignore the directions. The correct way is to do a vector addition of F12 and F13 using the parallelogram law. The answer will almost never be 10, unless both forces were pulling in the exact same direction, which they are not here. So to save your precious marks in the exam, please remember these 3 points. Call them your mark savers. Number 1, force is a vector. Say it with me. Force is a vector. It has both magnitude and direction. Number 2, always before you write a single equation, draw a diagram and draw the force vectors. This will save you from so many silly mistakes. And number 3, the force between any two charges is their private affair. The presence of a third charge, Q3, does not affect it one. All right, I really hope the concept is now crystal clear. So let's just do a very quick recap of what we learned, and I'll also show you why this principle is so incredibly important for our very next topic. You see this one by one and then do a vector sum idea? It's like a superpower in physics. Why? Because we are not just going to use it for forces. In our very next lesson, when we study the electric field, we will use this exact same superposition principle again. So if you master it today, the next topic is going to feel like a piece of cake for you. So what are the main takeaways from today? Let's summarize. First, to find the total force from many charges, we use the principle of superposition. Second, the rule is simple. Calculate each force individually, and then, very important, find the vector sum. And third, something for your conceptual questions. The force between any two charges is completely independent of the presence of other charges. And I'll leave you with a question to think about for our next class. We now know how to calculate the force on a charge when it's placed in a crowd. But what if we remove that charge? What exists in that empty space that's created by the crowd? How can superposition help us describe that space itself? Well, that something is the idea behind the electric field, which we will study next. See you in the next class. Bye, cartero.